Good morning everyone. I am Atharv Ashish Parab from School of Civil Engineering, and today I will be presenting on Introduction to Bridges, a fundamental topic in transportation engineering that reflects the harmony of civil design, structural design and public utilities. Let's move forward. Introduction to bridges. Bridges are now one of the oldest and most essential forms of civil infrastructures. They provide vital links across natural obstacles like river, valley, and uneven terrain. From ancient wooden logs to today's marvels of engineering like cable-stayed bridges, their evaluation shows how far our technology and thinking have come. Bridges not any connect places, they connect people, economics, and ideas. Next to the next slide. So, classification and types of bridges. The bridges can be classified in many ways. First is by function, such as aqueduct for water, viaduct for multiple spans, and bridges for highway or railway. Then by structures like beam, arch, suspension, and cable-stayed bridges. And each structure type has its unique design philosophy and load distributions. And by materials, including concrete, steel, timber, and modern compositions. The iconic example of include the Golden Gate bridges, a suspension bridge, and ancient Roman aqueducts, which are a classic example of arch design. So, what is the next? Next is components of a bridges. So let's break down a bridge in its parts. First is superstructure. In what you see, the deck, girders and trusses that carries the load. Second one is substructures, including piers and abutment that transfer the load to the ground. And third is the bearings, act as a mediator between the superstructure and substructures. Each component must work in harmony to ensure safety. For instance, the 2007 bridge collapse in the USA was caused by substructure failure, a reminder of how critical every part it is. The bridge name is I-35W. So next is loads on bridges. A bridge must withstand multiple types of loads. First is dead load. Dead loads are the structure's own weights. It's basically self-weight of that structure. Second one is live loads. The live loads includes vehicles and pedestrians. Basically, live loads are imposed loads on the bridges. And third one is environmental loads that such as the environmental loads comes from winds, earthquakes, and temperature changes. And fourth one is dynamic loads. The dynamic loads results from acceleration, braking, and impact. Designing for all this ensures the bridge can handle real-world conditions safely. Uh, let's move to the next slide. IRC load specifications. In India, we follow IRC, Indian Road Congress guidelines. IRC 6 2070 define clause of loading. In class AA for military and heavy vehicles. In class A for normal highway traffic. And in class B for lighter and rural roadways. Designer use combinations of these loads with safety factor to simulate extreme conditions and avoid failures. So let's move to the next slide. Concept of economical span. So one of the most practical design consideration is the economical span. This is the span length where the total cost including construction and maintenance is minimized. This depends on the materials used and the type of bridge. For concrete bridges, the ideal span to the depth ratio typically ranges from 12 to 16, and balancing structure efficiently and cost is a key skill in bridge design. So let's move to the next slide. Next slide is afflux, HFL, and scour depth. The hydraulic factors are also crucial. These are the hydraulic factors, by the way. The afflux in the water level rises caused by breach itself, and the HFL or high flow level is the peak water level during a flood. Third is scour depth. Measures how much scour depth measures how much material is eroded near piers and abutment. It's shocking to know that about 70% of breach failures in USA are due to scours. So understanding river behavior is just as important as structural analysis. So next is failure of breach in India. In India, breach failure often stem from poor maintenance, overloading, and scout. Some tragic example includes the Machu Dam failure in 1979 and the Kolkata flyover collapse in 2016. The NHAI and other authorities now focus more on monitoring and upgrading our aging bridge infrastructures. So next is prevention and maintenance. So first of all, prevention is better than collapse. Means prevention is more important for bridges. First one is regular inspections. Regular inspection helps detect early sign of wear or damages. And second one is rehabilitation. Rehabilitation like strengthening and retrofitting can extend a bridge life. Third one is bridge management system. This use a software to track structural health. And fourth one is new tools like remote sensing and drones help surveys hard to reach area efficiently, and preventive care saves lives and reduce long-term costs. Uh, so, conclusion of our today's presentation is understanding bridges involves more than just concrete and steel. It's about balancing design, safety, cost, and nature. Let's always prioritize safety, maintenance, and innovation in our future bridge projects. Bridges are more than structures, and they are symbols of connectivity and progress. Thank you. Signing off.